Ever look up at the sky and wonder what really drives our planet's weather? Well, it's not just random chaos. There's actually a massive, invisible engine constantly churning away above our heads. So today, we're going to pop the hood on that engine and see exactly how it works. So it all kicks off with this really simple but huge problem of balance. You've got the sun just blasting the equator with intense, direct energy, while the poles, they only get these weak, glancing blows. Now, logically, the tropics should just get hotter and hotter and the poles colder and colder, right? But they don't. So what's stopping them? The answer is our atmosphere, which acts like a global delivery service, constantly moving heat from where there's way too much to where there's not nearly enough.
But before we can even start to follow the heat, we have to understand the first and honestly the most important rule of the road for our atmosphere. And it's this: the Earth's spin changes everything. Because of that spin, nothing moves in a straight line on our planet.
This rule has a name, the Coriolis effect. Now, I know that definition sounds super complicated, but the idea is actually pretty simple. Just imagine trying to draw a straight line from the center of a spinning record out to the edge. Even if your hand moves perfectly straight, the line you draw on the record itself is going to be curved. Well, that's the Coriolis effect in a nutshell, and it happens to absolutely everything that moves across our spinning planet, especially the air.
So what's the big takeaway here? It's pretty simple. The Earth spins, that spin deflects the winds, and in the northern hemisphere, which is what we'll focus on, that deflection is always to the right. This simple right-hand turn is literally the key to unlocking the patterns of all the winds on our planet. It's a huge piece of the puzzle. Okay, so now that we have that rule in our back pocket, let's follow the heat. Our journey is going to start at the equator, which is the powerhouse of this entire system, inside something called the Hadley cell.
It is a beautiful, powerful convection cycle. You've got all this intense solar energy at the equator heating up the air, which makes it light and forces it to rise way up. High in the atmosphere, this warm air starts to travel towards the poles. But, it's kind of like a hot air balloon that's run out of fuel. It cools off, gets heavier, and sinks back down to Earth at around 30 degrees latitude. This sinking air creates high pressure, and from there, it's got to go somewhere. So it flows back along the surface toward the equator, completing the loop. And those surface winds flowing back to the equator? Well, they don't go straight, of course not. Thanks to our old friend, the Coriolis effect, they get deflected to the right. And this creates the steady, famous northeast trade winds. These winds were the superhighways for early sailors, making those long transatlantic voyages even possible.
Now let's just jump all the way to the other end of the world, up to the pole, where we find something that's almost a mirror image of this process. This is the polar cell, and it's driven by intense cold, not heat.
So up here, instead of starting with rising hot air, we start with sinking, brutally cold air right at the poles. This creates a dome of high pressure. That dense, cold air then spills out along the surface, heading towards the equator. Then, around 60 degrees latitude, it bumps into warmer air, gets forced up, and flows back to the poles in high altitude to sink all over again. And just like before, those surface winds flowing away from the pole get bent to the right by the Coriolis effect, creating winds we call the polar easterlies. So now we have two powerful self-contained circulation loops, one in the tropics and one at the poles, each doing its part to move heat around. But what about all that space in the middle? Now this is a really important difference to understand here. The Hadley cell and the polar cell, we call them thermally direct. They're true heat engines. They're driven by the fundamental physics of hot air rising and cold air sinking. Simple as that. But the massive space in between them, that's run by a completely different mechanism. The cell in the middle latitudes, it isn't a heat engine at all. A better way to think about it is like a passive gear, just being turned by the two powerful engines on either side of it. This is the Ferrel cell. Yeah, the Ferrel cell is what we call thermally indirect. It's essentially caught in the middle, just getting pushed and pulled into motion by its powerful neighbors, the sinking air from the Hadley cell and the rising air at the polar front. They basically force the air in between to circulate. It's not creating its own motion, it's just transferring it. But don't let that word passive fool you. This motion is incredibly important. As air on the surface tries to move from the tropics towards the poles, it gets deflected to the right, and this creates the westerlies, the powerful prevailing winds that are the reason storms generally travel from west to east across North America and Europe. If you live there, the Ferrel cell is the reason for your weather. So let's step back for a second. We now have our three cells, the Hadley engine in the tropics, the polar chiller at the top of the world, and the Ferrel gear stuck in between. Let's see what this whole amazing interconnected system actually accomplishes. And this
This is the solution to that big question we asked at the very beginning. This whole three-cell system is basically a planetary-scale conveyor belt. The Hadley and Ferrel cells work together to drag warm air away from the tropics, and the polar cell efficiently ships cold air away from the poles. It's this constant churning exchange that solves the Earth's massive heat imbalance, keeping the equator from boiling and the poles from freezing solid. It's what makes our planet livable.
For thousands and thousands of years, this elegant, vital system has kept our planet in a delicate balance, making life as we know it possible. But now it's facing a new challenge, which brings up a really crucial question for our time. This entire engine, it's powered by temperature differences. So as we humans fundamentally change those differences, how is this great balancing act going to respond? Just how stable is the engine that runs our world?